Hey guys, today I'm going to take you through some applications of the dot and cross products. So we're going to go over torque, work, and also the triple scalar product and its applications. So let's get started. The first application that we're going to take a look at is torque, which is essentially a vector that is the measure of a force acting on an object that causes it to rotate. So we're going to calculate torque by doing the cross product of the force vector and information from the torque arm. Torque is measured in units of Newton meters, and we like to use Newton meters for torque, and we've done some applications with work already, and we're actually going to differentiate these by using joules for work and Newton meters for torque. I think I accidentally mentioned in a previous lesson that I was going to do Newton meters for work and something else for a later application, but I was mixing it up. So Newton meters for torque, joules for work. Let's take a look at the torque formulas here. So if I'm looking for the actual vector for torque, I want to find a magnitude component, which is this component here, and I'm going to multiply it by the direction, which is the normal vector. So the things in this formula here, we have the force vector that's acting on the object. We have the radial distance calculated using meters from the pivot point to the point where the force is applied. We have the angle, which is going to be the angle between the vectors when arranged tail to tail. And we have the normal vector, which is going to represent the direction of the torque vector. Now, if I'm just interested in the magnitude part, I remove this normal vector part, and you can see that we're just interested in that magnitude component if I just want to know what that torque is, but not the direction. So let's take a look at an example here. A wrench is used to tighten a bolt. A force of 60 newtons is applied in a clockwise direction at an angle of 80 degrees to the handle, 20 centimeters from the center of the bolt. Calculate the magnitude of the torque. So you can see a visual of this over in our diagram here. And typically what we'll do is just slide this force vector over so that the vectors are arranged tail to tail. So I'm going to slide that vector over. And you should notice here, because this is literally the same vector, they are parallel, and we have a Z pattern, which means that these interior angles are actually equal. So whether the vectors are arranged tip to tip or tail to tail, they actually have the same degree value between them, but it is important that we arrange them tail to tail for when we decide on direction here. So that's going to come in a second. So in order to do torque, I'm going to do magnitude of force times magnitude of the radial distance in meters times the sine of the angle between them. So our force is 60 newtons. Our radial distance is actually going to be 0.2 meters. Okay, always make sure that that measurement is in meters. And then we're going to do the sine of 80. So if you're following along with your calculator with us, just make sure that your calculator is in degree mode. And let's round to 1 decimal place. We're going to get 11.8 Newton meters as the magnitude of our torque. Now, remember guys that the cross product of two vectors is actually a vector that is perpendicular to both vectors. So the wrench example is a really great example in order to kind of ground our understanding of the cross product. So if you imagine that you're working with a wrench on a bolt, the result is that as I work on that wrench, the bolt is either going to loosen or tighten depending on the way that I'm pushing the wrench, right? If I'm pushing it one way, it's actually going to be loosening the bolt and the bolt will be coming up. If I work on the wrench the other way, I'll be tightening the bolt and that will go into a piece of wood or whatever I'm tightening it into, right? So for part B, it asks us what direction does the torque vector point? In order to do this, we need to use that right-hand rule that I introduced to you guys in the cross product lesson. So the goal here is to take our right hand and we're going to line our right hand up with that radial distance vector. And here, the order of the cross product really does matter because that gives me an accurate idea of which way the torque vector is going to point. So I want to line my hand up always with the radial distance vector And then we want to be able to curl our fingers toward the force vector. So if I do this, I'm going to need to have my palm facing down in order to be able to curl my fingers toward that force vector, which is underneath the radial distance vector. It's also important that I slide this over and have the vectors arranged tail to tail for when I do the right hand rule, because if I tried to do that otherwise, I wouldn't quite know how to curl my vectors toward that, or how to curl my fingers toward that vector. So down, and I curl my my fingers, oh my goodness. I curl my fingers toward the force vector, and you should see that your thumb is pointing inward. And if we imagine that your screen or your paper is kind of like a piece of wood, that means our bolt is actually being tightened inward. So our torque vector is going to point into the page, which means our bolt must be tightening. The third part of this question asks us, what is the effect if someone were to grab the handle of the wrench 10 centimeters down and apply the same force? So we're going to change our radial displacement to, so if this is our wrench, we're actually taking the force and we're moving it down, which makes that radial distance equal to 10 centimeters. So the magnitude of the radial distance is now 10 centimeters. And the force is actually the same. So the magnitude of that force is still going to be 60 newtons. And when I arrange them tail to tail, they will still be meeting at an angle of 80 degrees. So when you go to find your torque, we'll just say magnitude here. Radial distance in meters times the force applied times the sine of the angle between the two vectors. So let's plug this into our calculator. We'll round to 1 decimal place again. Should be getting about 5.9 Newton meters. So let's compare that to what we got in part A here. What's the connection between 11.8 Newton meters and 5.9 Newton meters, and how does that relate to what we just did with the radial distance? Okay, so you should be noticing that what we found in part C is actually half of the magnitude of the torque that we found in part A. And we've actually halved the radial distance. So this actually should make sense that we get about half of the output in that magnitude of torque. Okay, let's take a look at some projection examples, and then we're going to do a work example. So projections in 3 space are very similar to what we did in 2 space. So we're basically just going to use that same formula, except now we have a z component. So we're going to find, given vectors v and u, we're going to find the projection of v onto u, which is going to be v dot u over u dot u times vector u. So the result from this is actually going to be a scalar, and then we're going to multiply that scalar by vector u. So v dot u, just to remind you, we multiply like components and then add them together. So this is what you should get. And u dot u, essentially that just means we're taking each component and squaring it and adding them together. And then we're going to take that result and multiply it by vector u, which is 368. So let's take a second. You can pause your video and calculate the answer here. So you should get 86 over 109 times your vector. Okay, so you can leave it in this format, or alternatively, if you want to distribute that into each component, you can do that as well. So if you do that, you should get this resulting vector. We usually just leave that in fraction form, and if you can reduce the fractions, you can do that as well. For the second piece here, we're going to find the magnitude of the projection above. And again, we're just going to reuse those 2D formulas that were introduced to us before. And when we do the magnitude of a projection, we actually want, we're going to get a scalar out from this, and we want to take the absolute value of that scalar to actually just find the magnitude of that vector itself. So this is going to be absolute value of v dot u over the magnitude of u. So we take out the direction component from above. So v dot u, we've already done this. This is 86, and magnitude of u can actually be calculated pretty easily off this. We're going to calculate this by simply taking each component squared and taking the square root of it. So what we get is root 109. And we're going to take the absolute value of that, which gives us 186 over root 109. Alternatively, we do have the actual vector itself already calculated in part A. So if you wanted to, you could also just take each component there and you could square it and add them and then square root the answer that you get from that. Or you can also simply use this scalar format over here and find the magnitude of that. So if we kind of separate these out into pieces, the scalar, of course don't really need to take the magnitude of that, but I will take the absolute value if that happens to be negative. And then you can basically just take the magnitude of the vector itself, which you've already really found in our previous calculation here to be the square root of 109. So essentially you just get what you got in the first version of this calculation, but you get the rationalized denominator version of that. So these are really both the same, but one has a rationalized denominator and the other doesn't. Let's take a look at a work application. So just to remind you, work performed is the product of the magnitude of displacement traveled by an object and the magnitude of the force applied in the direction of motion. So we can use dot product to find this, and when we take the dot product of a force in newtons and a displacement in meters, we get Newton meters, but we're going to use joules to indicate the units for work. So we haven't done a work application yet with 3D vectors. So let's take a look at how we can use 3D vectors and calculate the amount of work done. So remember that work is essentially just the dot product between a force and displacement vector. And if these are already set up in Cartesian format, they have a magnitude contained in there, and also they have a direction contained in there. So all we really need to do is find how those components are working together, and then we're going to find the sums of those products. So just take each component and multiply and add them. You're going to get 900 plus 700 plus 6,000 here, which gives us a result of 7,200 joules. That's going to be our work performed. Second part here asks us to determine the work done against gravity, which is basically going to be the force. So gravity is going to be the force in the direction of the negative z-axis if we think about our 3D quadrant grid. So this is our z-axis, which means that force of gravity should be going down in this direction. Now, in order to find the work done against gravity here, basically what we'll need is just those vertical components, which are the z components of the vectors. So I'm basically going to place, I'm still going to do the dot product to find the work against gravity. Oops. Maybe we'll just say AG for against gravity. And we are going to take the dot product of the force vector with the displacement vector, but I'm going to set the x and y components of these vectors equal to 0 to find the work done against gravity. So I'm just interested in that z component, which is 500, and the other z component, which is 12. So essentially you're just going to end up getting 0 times 0 plus 0 times 0 here, plus 500 times 12, which will result in 6,000 joules of work done against gravity here. Lastly, we're going to take a look at the triple scalar product, which is basically taking the cross of two vectors and dotting it with a third. Now, if we cross two vectors and dot them with a third, that expression would only be meaningful in one way. Let's say we take this A dot B and we did that first. Well, we know that the result of the dot product is actually a scalar. and then I would be trying to cross a scalar with a vector. So that combination here actually doesn't make sense. What we would need to do first is the cross product of the two vectors, which is the result, which has the result of a vector. And then I can dot that vector with vector A, and the result should give us a scalar. Now, the interesting thing about the triple scalar product is that it will give us kind of the same answer no matter which way we do it. So it will either give us the positive version of the answer or the negative version of the answer. But let's say our answer was 100. If we performed the cross product maybe with two different vectors and dotted it with a third, maybe we would get negative 100. So you'll always kind of get the same answer, but it might be the positive version of that answer or the negative version, depending on the order that you do the triple scalar product in. So let's take a look at an example here. We have three vectors, and we're going to cross u and v and dot them with w. So we're going to take vector u and write it out twice, one after the other, and vector v, write it out twice. And then we're just going to remove that first row and second row. We don't need those. And let's start our cross product. So we're going to do 3 times 6, which is 18, minus 5 times 1. And then for the second block here, we're going to do 2 times 1, which is 2, minus 6 times 4, which is 24. And 5 times 4, which is 20, minus 3 times 2, which is 6. Okay, if you start kind of calculating some of these in your head, be very careful when you get to things that have negatives and positives. So here you should get 13, negative 22, and 14. Now in order, so that was just, I guess I should have labeled that u cross b. Now in order to do the triple scalar product, we're going to do u cross b, now dotted with w. So that's going to be the vector that we just found, dotted with our w from above. All right, so there's our dot product, and then we'll just take a second to calculate it. And you should get 0. So this answer is actually significant here, but it's going to be more significant once we talk about the next part. So I'm going to hop back to this and explain what it means when the triple scalar product is equal to 0 after we do volume of a parallelepiped. So we can use the triple scalar product for this specific application, and that is finding the volume of the three-dimensional figure that could be formed by 6 parallelograms. And things like cubes are also considered parallelepipeds because they have opposite sides formed with technically parallelograms. So we can use it for things like that as well. So basically, to find the volume, we simply want to cross two vectors, dot it with the third, and because the result of the triple scalar product is in fact scalar, these right here actually don't represent magnitude, they actually represent absolute value. So basically, we're just taking the answer and we're making it positive. Of course, we know that volume needs to be a positive answer. And as I mentioned before, the triple scalar product will give us the same thing, but sometimes depending on the order that we cross the vectors in and dot it with the third, sometimes we'll get a negative answer, or sometimes we'll get the positive version of that answer. So taking the absolute value, just make sure that no matter which way we cross and dot in the combination of 3, that we actually get a positive answer no matter what. So let's take a look at an example. So you can actually choose any two vectors to cross here. So let's say we do A cross B, and we dot it with C. Okay, if you want, you can choose another two to cross first and see if you get the same answer. So we're gonna we'll write out A twice and B twice. And then we'll erase the first 2 lines, and then we're gonna find the cross product of each section here. Okay, so we're just gonna start with A cross B. So we're going to get 27 minus negative 12 for the first section here. Second section, we get 8 minus 54. And then third section, 36 minus negative 12. Careful with your negatives and positives there. Okay, we're just going to simplify that up. And you should get 39, negative 46, and 48. Now we're going to take that answer and we're going to dot it with vector C. So that means I'm taking this vector here and dotting it with the vector 3, 3, negative 11. So remember, the dot product means that we multiply similar components and then add the products. And you should get negative 549. Now, as I said, see how we get a negative answer here? That's why these absolute value bars are in fact important. I actually forgot to write them. So we'll make sure that we take the absolute value of that, which means that we get 549 units cubed. Okay, this is important to note that we are measuring in cubic units here. So that should be our answer for volume. Now, I said that I was going to hop back to this answer of 0 that we got for the triple scalar product. Now, if I imagine that I have these three vectors here and they create some kind of volume, well, if I get out 0 from the triple scalar product, even if I take the absolute value of that, I'm still getting 0. So if we imagine this in terms of our application, what does this mean about our three vectors? And what does this mean about this parallelepiped that can be formed by these three vectors? Well, really what this means is if I have a plane, okay, imagine a sheet of paper almost, these three vectors are all lying flat on this same plane. So they're actually not making a shape at all. They're just simply three vectors that are lying in the same plane. And actually what this means when we get the triple scalar product equal to 0 is that the three vectors are what we call coplanar. Okay, meaning they lie in the same plane.